let me start and recall what was the last time. So last time we almost classified all reducible finite dimensional presentations of the Lie algebra SL2 over complex numbers. And the main result that we had was the following. So suppose that we have V. Okay, as I said, it's finite dimensional representation of SL2C. Then, and also, I would like it to be reducible. So maybe let's go. Then there exists unique number lambda, which is actually natural or zero. And a vector V in V such that V is killed by the action of element E in SL2C, and V is eigenvector for H with eigenvalue lambda. Right? Then lambda is called highest weight of V, and V is called highest weight vector. And such V is called a representation of highest weight lambda. And also we figured that if I have two isomorphic representations, V and W, then the corresponding highest weight is the same. Right? And so therefore we have a map. Let's call it L. It is from isomorphism classes of finite dimensional irreducible representations of SL2C to non-negative integers, and it takes a representative of a representation and gives me highest weight. And we stated the following. Okay, let's state it as a theorem, I guess, is that the map L, so this one, is a bijection. And it is almost obvious out of what we did last time. All right. So proof right. So proof is the following. Let me just take. Well, first I need to prove that it's injective, right? So L is injective because of what? If I have two representations, V and W, and these are finite dimensional reducible representations of the same highest weight, then I would like to see that they are isomorphic, right? But then we figured that, okay, I have highest weight vector here, highest weight vector here, right? Then I have the following basis: f applied k times as k runs from 0 to lambda, and corresponding basis in w, right? K from 0 to lambda. So these are bases in v and w respectively. Right, so let me define this as vk and this as wk. Then I can just define linear map phi, which sends vk to wk. And this will be isomorphism of representations of v and w as representations. Right? We just check that any elements E, F, and H, they act the same on VK and WK. And L, so this proves that L is injective, right? And L is surjective. Well, you can do it in different ways. They're all simple. You can just state the following. You can just say that, so surjective means that for every number here, I need to give you a representation of this highest weight, right? And so, so for any lambda from there, I just state that S lambda C2, so it's lambda symmetric power of C2, is a representation of highest weight lambda. And okay, this we'll check on the seminar. The other way is just to remember what we got last time, right? So remember that, so okay, so if I have V, then I have this unique pair lambda and V small, and basically then I know everything about this representation V, right? Namely, again, if V rep of highest weight lambda, V highest weight vector, then actually we can just draw a diagram how everything acts on V. So I have lambda plus 1 dots, right? Each of this dot represent, so this is V, right? This is FV, this is F square V, and so on. And the last one is F lambda V, right? And so F just acts like that. It just jumps, it just sends V to FV, FV to F square V. So this is how F acts. And it gives, if I apply F, obviously I get exactly this vector. So it acts, it gives me this vector with coefficient 1, right? So if I go all the way to this point and try to apply f, this will give me 0. Right? On the other hand, E works the other way, right? So E is here. And here it gives me 0. But not with coefficient 1, right? So if I take this sum vector here, for example, I don't know, f k. So this was another computation that we had. Then I obtain f k minus 1v, but not exactly, but with some coefficient, right? And this coefficient was k times lambda minus k plus 1, and we proved this by induction. So we just have basis, we have, and we just described completely how f int a, okay, h. And h is just, we never moved from this dot, so h is like that. And so h, I appear at the same point, again with some coefficient. But with which coefficient? Okay, just to check that you're awake, let me ask you. So what coefficient I should write here?
The number k.
What k? So k is here. So here is just lambda, right? So this is highest weight. And here, right, hx with eigenvalue lambda minus 2k. So we know everything, how h, f, and e works. So another way to see surjectivity of L is just say, okay, I give you lambda plus 1 dimensional space with the basis v, v1, v2, and so on, vk, v lambda, such that E, F, and H act like this. And I claim that then this is representation. And this is representation just by construction. And this is representation of highest weight lambda. So you can just say, just use all that work that we did last time and just constructed representation using the results that we had before. Okay. All right. That's everything for now that I wanted to say about SL2. So the next, let us start the next topic, which is so-called universal enveloping algebra. So you see already here, when I was trying to construct representations of SL2, I am writing already f to the power k. So it is not multiplication in SL2, right? It is actually multiplication in the representation already. So this thing, right, when I write something like this, I really mean rho of f, and then I take power k. Right? I apply rho of f, k times 2v. Right? It is not the same. It's not the same thing as if I just consider f as a 2x2 matrix, consider k power of it. Right? F, for example, is 0, 1, 0, 0. Its square already is 0. Right? So it's not the same as taking this as a 2x2 matrix, take it to the power k, and then apply it to v. But this is actually multiplication. This can be said without representation, right? This makes sense without representation, but in some associative algebra, where I have multiplication, which is called universal enveloping algebra. So the main, one of the main reasons is sometimes it's easier and more useful to work with associative algebra when you think about the representations than about Lie algebra. And this associative algebra is what we are about to construct. All right, so we start. So let G be again some Lie algebra. And maybe even infinite dimensional. Then I would like to consider tensor algebra of G, which is the following thing. It's a direct sum of all tensors, k-fold tensor products of G. You can do this with any space V, right? So it is an algebra with multiplication. Hey. So what is multiplication here? Multiplication is, so for any A and B in T of G, I just multiply M of A, B, or I can just write like this. It's just A tensor B. So this thing is naturally a graded algebra, and it is as free as you can as you can require for a vector space G, right? So, anyways, so you have tensor algebra. And then you can consider two-sided ideal. So that J be two-sided ideal in T of G, generated by the following elements. So X tensor Y minus Y tensor X minus XY for any pair of elements from the Lie algebra G. So what does it mean, two-sided ideal?
It is multiplied on both sides and still be.
Yeah, yeah. So if it's a some element which consists of products of things, right, and one of the factors in this product is this, then it's zero. Then it's in this ideal. Sorry. Okay, and so since it's the two-sided ideal, I can quotient by it and get another associative algebra which I denote by U of G, and this I call universal enveloping algebra of G. Okay, so the first question we are about to answer is why it's called universal. So it's called universal because of this property, proposition. So suppose, so it's universal property of U of G. And proposition says the following: let A be an associative algebra such that I have additionally homomorphism of Lie algebras from G to A. It's a homomorphism of Lie algebras. So what does it mean? Right, this Lie algebra, why this is Lie algebra? Yeah, so commutator is so associative algebras are naturally Lie algebras if we in Lie bracket is commutator. So commutator Lie bracket here is brought by phi to commutator here. Then there exists unique homomorphism of associative algebras from U of G, so let's call it psi, to A, such that the following diagram commutes. And the diagram is like this. So you have U of G, send it to A by psi, and then you have G, you send, you send A to G to A by phi, and you send G to U of G somehow. So let this map, let us call it epsilon, right? And so you have G, which is summand in here, right? Of degree 1, right? So you map G to T of G. And this is possible because you just, it's actually you include, right? And then you project. And this is epsilon. So where, I should write where epsilon is this map. Okay, the proof is pretty simple. Right. So I just need to define this psi on generators, right? So I have, actually in U of G, I have generators. It's generated by the image of epsilon, right? So I take, abusing notation, I'm just consider elements of G already of elements of U, right? Just think of image of epsilon. And I need to define psi on these elements. Right? Is it clear why it generates the whole U of G? So you see T of G is this thing, right? So if I take k equals 0, it's just C, right? So it just if you multiply, it just stays C. So if you take k equals 1, which is G, and you start multiplying, it gives you all other k's, right? So G actually generates T of G, and the image of G in U of G generates U of G then. Okay. So I just define psi of of epsilon of x to be phi of x for every x in G. So I claim that this is well-defined map. So claim is that it is well-defined homomorphism. Psi is well-defined homomorphism of associative algebras, right? So psi is from U of G to A. And so we just need to check that it satisfies the only generating relation that we have in U of G, right? Mainly, if I take epsilon of x1, epsilon of x2 minus epsilon of x2, epsilon of x1 minus epsilon of x1, x2. If I apply psi to this thing, then this becomes 0. But this is so epsilon of x1 times epsilon of x2, right? This what I claim is that this follows just from the fact that phi is homomorphism of Li algebras. So if we say that if we define it on generators like that, and say it is homomorphism, right? Then this really should is the following thing: psi of epsilon of x1, psi of epsilon of x2, minus psi of epsilon of x2, psi of epsilon of x1, minus psi of epsilon of x1, x2. But this is, by definition, just phi of x1, phi of x2, minus phi of x2, phi of x1, minus phi of x1, x2. But this is 0 because phi is homomorphism of Li algebras. So we proved that if we define it on generators and try to extend it by saying that it is homomorphism, then it respects relations in U of G. So therefore, it's well defined. So therefore, it's well-defined homomorphism from U of G to phi to A. And moreover, we just put by hands that just by construction it commutes with such. This diagram is commutative. Okay. So I'm kind of writing epsilon of x every time. Every time I'm thinking of an image of G in U of G. Because we don't know yet that epsilon is injective. Right? But it is actually true, and it is not obvious at all that that epsilon is injective. And G is the Li subalgebra in U of G. So after we will prove it, and this is corollary of what is known as Poincare-Birkhoff-Witt theorem, we'll just never write these epsilons and think of G as a subalgebra, Li subalgebra in U of G. All right. We didn't prove uniqueness. Yeah, so it's a unique maps that such thing well, if you would like this diagram, okay, let me recover it. So you have U of G, you have phi, you have A, you have G, you have phi here, and you have epsilon here. So suppose that you have such thing, then on generators on epsilon of G, since this diagram is commutative, it should be exactly like this. So there's no other way to define it rather than this. Right, so next, now I would like to make the following easy observation is that representations of G are representations of U of G in the other way around. Representations of U of G are representations of G, right? So let V be a representation of U of G. So U of G is an associative algebra. What does it mean to have a representation of associative algebra? It just respects multiplication, right? So basically, multiplication and sum, if you wish, right? And linear structure. So if V representation of U of G, so what does it mean? That is, there is a homomorphism of associative algebras ρ from U of G to linear transformations of V. Then this pair V and homomorphism ρ precomposed with epsilon. Then this is representation, of course, of G. Right? So I have G by epsilon, it's mapped to U of G. And then I have ρ, which sends me to endomorphisms of V. And the fact that ρ is a representation of U of G says that actually if I have epsilon of x1 times epsilon of x2 minus epsilon of x2 epsilon of x1 minus commutator, it goes to 0. So it's the same as commutator in here. So this means that rho is representation of u of g, right? But this exactly means that then it is representation of g. Okay, and the other way around, so conversely, if V representation of G, then so if V is the representation of G, then I have homomorphism, right? So there exists homomorphism of Li algebras. Well, let's call it phi, right, to match what we have there, from G to endomorphisms of V. Then by universal property of U of G, there exists homomorphism of associative algebras. So my A now is endomorphisms of V. Psi that sends U of G to endomorphisms of V. And it's, I mean, it's a very easy or almost trivial exercise to check that if I have like homomorphism of representations of V, then it's a homomorphism of representations of U of G, then it's homomorphism of representations of G, and the other way around. And so, so this, so actually, we can state now that representations of U of G, like category of representations of finite dimensional representations of U of G, and category of finite dimensional representations of G is just equivalent. Okay, and Stysing representations of G is the same as Stysing representations of U of G. And now let us state famous Poincare-Birkhoff-Witt theorem. Or it's usually like in many papers, it's just this PPW theorem. It states the following. Let me choose an ordered basis in G. So let x1, xn be a basis, in G. Yeah, so now I'm silently assume that G is finite dimensional, but this theorem is very holds in much more general situations. For infinite dimensional Lie algebras, for Lie algebras over various fields, not only R and C, but like over fields as well. You can consider some Lie algebras over rings, but not all of them. So it's actually like there's a whole business of, you know, different proofs of Poincare-Birkhoff-Witt theorem. So if I, so we will prove only for finite dimensional Lie algebras. Okay, so in finite dimensional Lie algebra G. Then the following set of monomials x1 to the power k1, x2 to the power k2, x k to the power kn. Here ki are non-negative integers, is a basis in U of G.
There should be xn in power kn.
Yes, xn in power kn. Yes. Okay, so let's prove it. So there is an easy part and harder part. Easy part is to prove that B is a complete set, so that B spans U of G. So first, let us prove that B spans U of G. So we actually can, for any monomial monomial is just in U of G. So you see, this is a multiplication in U of G. I'm just stressing here. So it's not commutative, right? So if I replace it, I should also add commutator. Actually, this is my rule in U of G. So monomials are not only like this. So any monomial, it can be of the form like this: xi1, xi maybe ik, and k here is not necessarily n. So mk. So any monomial like this, we can define its degree as m1, so just sum over mi's. So we actually know that if I write xi1, xi2, so I can actually change the order and write xi2, xi1, but I have some correction terms, which is, but this correction term is linear. So it is sum over I from 1 to n xi with some coefficients ci, which of course depends on I1 and I2. Right? because of this, so we have such relations. So this is what's called structure constants in my Lie algebra, right? So this is a relation in Lie algebra, right? It's a commutator. I can take any monomial xi1, m1, xi2, m2, and so on, xik, mk, and write it in the way that I need, in this way. So x1 to the power k1, x2 to the power k2, xn to the power kn. So I'm using, so I start permuting x. So at the end, I will end up with such thing, right? And so plus some correction term because of this. But these correction terms will be monomials of degree less than sum over mi's. But this, so sum over k a from 1 to n, is the same as sum over, so degree of this monomial is the same as degree of this monomial. And then just repeating this process. So since for every monomial it has some finite degree, right? So at each step I decrease degree at least by 1. I will write this in this form, right? For some other case, right? And so on and so on, and finite number of steps. So any monomial can be written as sum with some coefficients of monomials of such sort, right? So infinite number of steps, we will write P, so let us call this P, as a linear combination of elements from B. Well, since any monomials, they span U of G, of course, right? So U of G is sums of different monomials of such kind. Therefore, and every monomial can be written as linear combinations of these special monomials, like this, ordered, where I choose order. So therefore, B spans whole U of G. So therefore, B, so U of G, this is span of B. Okay, so this is an easy part, which is completeness of B. And the harder part is to prove that B is linearly independent. So 2, B is a linearly independent set of elements. Okay, so here we will use the fact that our G is finite dimensional, and actually, therefore, there is a Lie group G with such Lie algebra G. And we have Lie algebra of left invariant vector fields on G, and which is isomorphic to the Lie algebra that we started with, right? So we have G is isomorphic to left invariant vector fields on G. So this is a Lie group with Lie algebra G. Right. So elements of these things are linear transformations of smooth functions on G, right? So I can actually take I can just take these linear transformations and generate an subalgebra in all linear transformations of C infinity of G by these elements. And this will be called differential, left invariant differential operators on G, right? So let dl of G be the associative subalgebra of endomorphisms of C infinity of G generated as an algebra by vec L of G. Okay, so we have actually right. So if this isomorphism, I don't know, let us call it how, I don't know, phi 1, right? And you have vec L of G is you have inclusion, right, of this into this. And this is Lie algebra homomorphism, actually, right? And so, and you have also G mapped to here by phi 1. So, I don't know, phi 1. So the composition, let us call it phi. So in other words, dl of G is an enveloping algebra of G. So it's an associative algebra such that we have homomorphism of Lie algebras from G to dl of G, right? So therefore, by universal property of U of G, there exists map psi from U of G to dl of G capital, right? Well, such that the corresponding diagram commutes, right? So let me not write it one more time. So idea is to show that images, so I have my B, right, which are monomials of this. I can send them by psi from U of G to here. And idea is to show that images of these monomials linearly independent in here. Since they are linearly independent in here, and this homomorphism of associative algebras, they're linearly independent in here as well. So to see that, we can just work in a chart. So choose coordinates y1, yn, coordinates on G around identity in G, such that, well, I have a basis here, which is x1 and so on, all the way up to xn, and I want image of this. So at least at point E, in these coordinates, I want x1 to be dy1, x2 to be dy2. I can choose y1, y2, at least at point 0, right? But in this map, this choice will look like this, phi, because so these are not so G. So I choose derivative at a point and then map it to like a derivative at like a I have a lot of derivative at many points, right? That's what vector field is, right? Anyways, so what I'm saying is that I would like my coordinates to be like this, that f of xi is dy plus, so if I would like, so if I want it just to be at point E, I can just, do it like this. If I would like some vector field in the whole neighborhood, I need to write something here. So sum of some coefficients which depend on my coordinates. So this is smooth function actually of y, and this is I from 1 to n. dy, so okay, I is here, so maybe j is better. dyj. And what is important is that I can choose age of all zeros to be 0. So such that again, so what happens here is that I'm choosing my coordinates such that at the point 0 is just x corresponds to derivative with respect to corresponding coordinates. But globally on my neighborhood, I cannot require that. They will deform somehow if I go outside of 0. But at 0, my coefficients will just vanish. Okay. And then phi of x1 of my monomial. Right, okay, so phi is from here to here. Then I take psi, right? I rather should take psi of my monomial xn to the power kn. So this will then be, since this triangle diagram commutes, this will just correspond to multiplication of these differential operators of first order. So I will have dy1 to the power k1, dy2 to the power k2, and so on, dyn to the power kn plus some mass I don't actually care about. Right, so plus d tilde, so let me, of y1, yn. And where d tilde, so this is differential operator, but d tilde of zero of zeros so what's important, this is differential operator actually of total degree smaller than so of degree smaller than sum over ki's, I from 1 to n. I wanted to write d of tilde of zeros is 0, but this is not exactly true because so what happens, yes, is that I will have something like dy, then h, then another dy. And then I try to commute, I will have some derivatives, right? So when I commute, either dy goes through, and then I have h itself, which vanishes, right? Or dy commutes with h. I cannot say that derivative of h is at 0 is 0. But when I commute, I will lose one derivative. So it's of degree less, right? So that's why I have this this claim. Okay. So we would like to see, and I don't know, let me call this thing dk, where k is a vector consisting of these numbers, k1, kn. This is just a notation. So we would like to prove that dk's are linearly independent. So we want to see that dk, where k is from z greater or equal than 0 n times, is linearly independent. Okay, so usually how do you do that? You just suppose that you have some linear combination of those, just arbitrary. So consider some d, which is, I don't know, ck1, dk1, and this linear combination is, of course, finite linear combination. ckm, dkm. So these are just some complex numbers or real numbers if you over reals. Then I would like to choose an order in here. So choose lexicographic or alphabetic, I don't know, lexicographic order on z n greater or equal than 0. I can reorder these d's in such a way that k1 is the largest element in this order, right? So let's assume, without loss of generality, assume that k1 is greater than, I mean, if it's equal, then they're just equal. I mean, yeah, so if it is equal, then they just equal. So, and then I just have another c. I mean, I can not write greater or equal here. So k1 is greater strictly than ki's. I is from 2 to m, and these are vectors. Okay. Then I claim, so then I take D and apply it to the following monomial in y's. y1 to the k1, y2 to the k2, yn to the kn, where these are elements of the vector k1. So k1, here's k1, k2, kn. So I apply and then put all y's to be 0. Then question is what is this thing then?
C1?
Yeah, this ck1 with some combinatorial coefficient which is not 0. Actually, what k1 factorial, maybe k2 factorial, something like this, right? So it's just a product of ki factorials, I from 1 to n, yes, ck1 vector. All others will be killed. It's either there will be no, not sufficient derivatives to kill it, or too many, or I will kill it, or but when I will put y equals to 0, corresponding coefficients of this part will be 0. So it's just so only monomial that will be non-zero, that will be it will be this one. I mean, applied. So this applied to this thing will be 0, and this one will give me just this coefficient times something because I differentiate number of times my variable. So it means that if for some reason I have some linear, non-trivial linear combination, which is 0, right? So a non-trivial linear combination, and I would like all ck's to be non-zero. But then it's then my coefficient for the largest k is 0, which is contradiction, right? I choose all of them to be non-zero. So if d equals 0, so therefore ck1 is 0. So there's no non-trivial linear combinations D such that D is 0. And this is exactly linear independence of dki's. So we actually proved that dki's are linearly independent. And therefore, images are linear. So if these things were linearly dependent, right, then by psi, I would, transfer this linear dependence to dk's, right? But since I know that dk are not linear independent, so therefore, right, these are linearly independent, and we proved Poincare-Birkhoff-Witt theorem.
Characteristics of the field is not 0, then this doesn't imply that the CK.
Yeah. So something, yeah.
But they always span
They do.
because we haven't.
Yes, spanning part is just linearity of the bracket. So to prove, it's very, there are very beautiful proofs of Poincare-Birkhoff-Witt theorem and very conceptual. So actually, you can. So the most beautiful one that I know is that by Braverman and Gates-Gorey. So they actually, so Poincare-Birkhoff-Witt theorem is actually about what's called flat deformations of symmetric algebra over G, of S of G, right? So you can, so if my J, if my bracket is just trivial, right? I take T of G, right? And my J, the ideal that I quotient by, is just this, right? So if my bracket is just 0, right? And then U of G is just S of G, just symmetric tensors. So in this way, U of G is a deformation of S of G. You can introduce like a parameter and say that x1, your J will now depend on parameter, and it will be like this. So if T is 0, it is S of G. If T is 1, then it is U of G. Right? So this is for abelian G. If it's not abelian, then U of G is some deformation of S of G. And so we would like to prove that actually, so this is now some module over K of T, and we would like to prove that it is a free module. And so actually, any bracket gives you like this transformation over K of T over T squared, only like linear. But abstraction to lift this deformation of S of G over K of T is exactly Jacobi identity. And this is the beauty of it. So basically, Jacobi identity plays the crucial role in linear independence, in hard part of this thing. And so the proof of this is homological. So usually you use homology in some degree to construct something for linear world, and to lift it up you have some abstractions that live in other homologies. And the absence of this abstraction is exactly Jacobi identity. Okay, so this is some, side note. So we used some geometry, and I mean our proof, the clue point of the hard part is that G is isomorphic to left invariant vector fields, right? Which is also we kind of work hard to prove that, and so now we're kind of using it. All right. Okay, so we have some time. Let me now take our knowledge about universal enveloping algebra and say something about more about the presentations of SL2.
Is it true that since we proved that this universal enveloping is isomorphic to left invariant vector field, this means that as an algebra it is spanned by its degree 1 complement, yes?
Yes. So basically, so again, from PBW theorem, right? We know that epsilon that we had now is injective, right? Because well, just linear x1, x2, and xn, these are monomials, right? From our B, so they should be linearly independent. So therefore, this epsilon is injective. In some proofs of PBW theorem, is the starting point. Actually, it's very non-trivial. It's kind of to prove that is the same almost to prove Adder theorem, that we have faithful representation. Yeah. So yeah. So now we can just never write this epsilon and think of G as a Lie subalgebra in U of G, in particular. Right, so maybe before SL2, let us make the following observation. So we actually now can, construct a bunch of maps which are isomorphism of vector spaces, right? So if I have x1, again, xn basis in G, well, I can consider S of G. So I just told you what it is. So again, it is T of G. So this has all symmetric tensors, right? It can be described as this: T of G quotient by two sided ideal GS, JS, where JS is x1 tensor x. So it's generated by this. So these angles mean that it's generated by two-sided ideal, which is generated by such elements where x1 and x2 are any elements in G. So these are really polynomials on J star, on dual to J, not J, G, I mean, right? Okay, so so now we can construct a lot of maps. For example, I can take phi 1. I take any monomial here. So this is basis in here, right? And I can actually permute x1s, xi's freely in S of G, right? Because this is my relations. I can permute them. This is basically what I say, right? But I can send it to the same exact order, to this. So this now multiplication not in S of G, but in U of G. And I cannot permute them freely, But PBW theorem says that this is isomorphism of vector spaces. So these are two infinite dimensional vector spaces actually, right? But we have still isomorphism between two infinite dimensional vector spaces. I can choose any other order. I can choose, I can send such thing, to xn to the kn, and this will be different map. Or I can just take and be very and make like a maybe canonical in a way choice. I just can take, not even fixing a basis, I can just any monomial. So this so yi, so maybe not n, maybe some k. Yi as just some, just any elements of G, not exactly a basis. And I can take this and send it to like a symmetrized version. So 1 over, k factorial, sum over permutations in Sk, and then I should write y tau of 1, y tau of 2, y tau of k. So this also by PBW theorem will be isomorphism of vector spaces. Well, you should check first of all that this map is well defined, but this is obvious, right? So the only check I should have is that if I take y1, y2 and replace yi and yj, just replace them, this will give me the same result. Because I symmetrized, of course the formula will be just the same. So this is the only check, and this is why this map is well defined. But also in each sum like that, so you just check that you hit. So if you take linear independent things here, right? For example, monomials like that, this will give you linear independent things here, right? By PBW theorem. So you'll have exactly one term from your PBW basis in each sum like that. Taking different monomials here, you will get different, like all elements in the PBW basis. So therefore, it is an isomorphism of vector spaces. Anyways, so it's harder to say it by words than just to sit down and check. So I claim that this is, by PBW theorem, this is also an isomorphism of vector spaces. But moreover, sigma, so first claim is that phi1, phi2, sigma, they are isomorphisms of vector spaces. But sigma is better than any other choice, because sigma is also an isomorphism of representations of G. So first of all, let us realize, so when I say representations, I should have G action here and G action here, right? What is this G action? Well, I of course have G action on T of G. So G acts on T of G. Just why? Because G acts on itself by just adjoint representation, right? And so take add, and then G sits inside, and then you take adjoint representation, and then expand it to the whole T of G by Leibniz rule. Okay, then extend it by Leibniz rule. Okay. But then you should check that, well, you have this ideal J. Well, let's start with this one, JS. So I would like to see that X acting on JS is still in JS. So this ideal is invariant with respect to action of G. So this is for any X in G. Well, what should I check? I should take just not to mix X with so let me take rather Y here to match my notation. So I have Y acting on element in here, on generating element. So it will be by Leibniz rule, it's something like this. Tensor x2 plus plus x1 tensor y acting on x2 minus y acting on x1 tensor x2 minus x1 tensor y on x2, right? So this is just what? This is just y acting on x1 tensor x2 minus x2 tensor x1, right? I just by Leibniz rule it's like that, right? But this is the same as, so I have yx1 tensor x2 minus sorry, I think, so I should have like this, x2 x1, right? x2 x1 here. So then I look at these two terms, right? So I have yx1 tensor x2 minus x2 tensor yx1. It lives in JS. So these two terms. And these two terms, x1 tensor y on x2 minus y on x2 tensor x1. This also lives in JS. So I have sum of two terms that lives in JS, so therefore it is in JS. And in U of G, right, you have another ideal. So U of G is T of G quotient by J, and J is generated by x1, x2 minus x2, x1. Right. and minus x1, x2, right? So if you apply y, so again, if you apply y to such thing, again, you just compute by Leibniz rule, and I will just give to you the answer, just not to do it on the board, so just exercise maybe. So I will get yx1, x2 so plus x1 y x2 minus y of x1 x2. So these are dots. But why this is 0? I mean, yeah, so this is just 0, I claim it. And the question is, why is this 0?
By Leibniz rule? Oh, by Jacobi identity.
By Jacobi identity, right. So y acting on x is just commutator. So if you just replace this with commutators, this will be exactly Jacobi identity. And any action is just J is just vanishes by action of G, really. So of course it's invariant. 0 is inside. So therefore both U of G and S of G. So I can quotient. So T of G is a representation. Both ideals that I quotient by Js and J are invariant with respect to action. So if I quotient, I still have representation. So these are representations. Moreover, U of G in U. So we figured that G are elements in U of G, right? And the action on U of G that we got. Just you can check that it's just commutator, right? So G is now element of U of G. So action of G on some element of U of G is it's a commutator inside U of G, right? If you try to commute, you'll get exactly Leibniz rule.
Commutation in sense of multiplication
In U of G, right? So it's just another way how to introduce it. All right, and so therefore both U of G and S of G are representations of G. So I claim again that sigma is isomorphism of representations. Again, this is some check, just computational thing. So it's proof exercise, or I don't know, maybe we can leave it for the seminar. But I mean, on the seminar, it's not also not very. It's just some computations. I don't know. Right. And why is that good? Is because, so from this claim, I can now figure out that there is isomorphism of vector spaces, the following. Center of U of G, which is a very important thing in representation theory. Because it acts by different numbers on different reducible representations. Is isomorphic to S of G invariant with respect to action of G. So as I said, U of G is a representation. So the representation structure on U of G that we defined is the same as that I think of G as an elements in U of G and just compute, right? But since G are generators of U of G, right? Everything that commutes with a G in U of G, right? So these are invariant elements with respect to this action, is actually commutes with everything. So this is exactly the center. But since sigma is isomorphism of representation, that corresponds to everything that under action of G becomes 0 in here, right? So these are all so these are elements that turn 0 under action of G. Or, yes. And this one is usually easy to compute. This is just, I don't know, some symmetric functions. And we'll see some exercise next time. That you can actually see what is this thing. And then if you know the, now you know the isomorphism just explicitly, you can compute the center of U of G. Okay, so let me stop here.